Broadcast is now starting. All attendees are in listen-only mode.
Hi, and welcome to today's SFP webinar on October 2017 wildfires. What happened, and can we map areas where it could happen again? This is Louis Garazzi, SFP's Manager of Professional Development, and I will be moderating today's webinar. Before we get started, I'm going to go over some information in regards to the webinar logistics. First, all participants will receive a certificate of attendance for 1 PDH. To receive a certificate, you must stay online for the entire webinar. Certificates will be sent out via email in about 1 week. Also, we do not provide copies of the speaker's PowerPoint presentations. However, we will be posting a video of this presentation on the SFP's YouTube channel and website in the next week. Additionally, you can ask our speaker questions by writing it in the webinar dashboard. You may ask a question at any time. However, we will not be taking any questions until the end of the webinar. Today's speaker is Chris Lautenberger. Chris is a fire protection engineer based in Northern California. He received a PhD in mechanical engineering from the University of California at Berkeley and a master's in fire protection engineering from WPI. His areas of specialization include materials, flammability, fire modeling, and forensic fire reconstruction. Chris has co-taught master-level courses in fire dynamics and fire modeling in the Department of Fire Protection Engineering at California Polytech State University, San Luis Obispo. So with that being said, welcome, Chris.
Good morning, everyone, or for some of you, good afternoon or evening. Thank you for joining. And I wanted to give a brief overview of what I'll be talking about today. Really, there's two separate parts. The first part, I'll talk about wildland and wildland-urban interface fires in California and explain why California has such bad fires, and then talk about some specifics from the October 2017 fires. The second part of the talk has to do with mapping areas that are at elevated risk of experiencing such similarly damaging fires. So we'll talk about wildland fire modeling, talk about some of the inputs and how we use this system to quantify risk and then compare to historical damaging fires. Part one, why does California have such bad fires? Here on the left is a plot showing the historical occurrence of fire in California from the early 1900s through modern day. On the right, what we have is housing density or development. And if you sort of mentally overlay these two plots, what you'll see is that there are large parts of the state where we've had historical fires occur and also where people live. So the short answer to the question of why does California have such bad fires is that basically people live and work and play in areas that are fire prone. And there are some specific characteristics of California that exacerbate this problem. On the left, we have the distribution of precipitation across California. So the northwest part of the state, Del Norte County, receives a significant amount of precipitation, over 125 inches a year, whereas the Mojave and Sonoran deserts in the southeast part receive very little precipitation. Now, California, like many of the western states, has a non-uniform distribution of precipitation throughout the year. Most of the precipitation falls in the late fall to winter to early spring months, and then by May or June, there's very little precipitation across most of the state. Now, another factor is that at the end of this 5 to 6 or 7 month drought in October and November, that's when the Santa Ana winds, or in Northern California, the Diablo winds start to occur. So these are winds that blow rather than from the Pacific Ocean into California, they blow the other way. They blow from the east to the west, or really from the northeast to the southwest. And many of the damaging fires that have occurred in California have occurred under this type of wind, which is sometimes called a phone wind. Now, if you've been to California, you know there's quite a diverse range of vegetation. So this is typical Sierra Nevada timber and understory, where we have surface fuels and under certain situations, fire burning through these surface fuels can make their way into the crowns where we have torching and crowning that can lead to long-range spotting and so on. And much of the Sierra Slope is, during the summer months, fully cured grasses. So because it doesn't rain for 5 to 6 months, most of the fuels by the time we get into June or July have reached this fully cured state. And if we go to Southern California, this is a typical type of fuel complex in Southern California where we have southern chaparral. And so this fuel type supports very rapid rates of spread, long duration spotting, long distance spotting, and can be very problematic from a fire control standpoint. So California really has this combination of fuels, weather, topography, and then people living in areas where those conditions are such that rapidly spreading fires can occur under certain conditions. So you put this all together, and it's really not surprising that we have these large loss fires. Now, I'll talk about the 2017 California fires, and specifically what's called sometimes the North Bay fires or the wine country fires. These occurred in October of 2017, but before I get there, I want to talk in general about the 2017 California fire season. It started off fairly typical. So I've plotted fire perimeters from all fires in California in 2017 in two different ways, one showing the land cover or ortho imagery on the left, and then the other is just a little more austere depiction where we just have county borders. So these are all the fires that occurred in California, and just in terms of some numbers for 2017, these were the fires through October. This is fairly typical fire season. This is the type of thing that happens every year where you have a few fires that burn a few thousand to a few tens of thousand acres. So we have Detwiller at 82,000, 63 homes were destroyed. Ponderosa fire destroyed 32 homes. The Helena fire, 72 homes. So these are fairly typical numbers. This is the type of thing that happens almost every year in California. Now, the situation changed significantly on October 8th. This was the day that a wind event that I'll talk about in a little bit impacted much of Northern California and ignited or caused several fires to be ignited. Now, these fires all spread very rapidly and were quite damaging to several areas and destroyed many thousands of homes. So just to put these numbers into context, whereas we saw for the fires prior to October 8th, 10, 20, 50, 100 structures destroyed. In these fires, those numbers increased by orders of magnitude. So Tubbs is about 5,600 structures. This is the Tubbs fire right here. The Nuns complex was about 1,400 structures, Redwood Valley over 500 structures, and so on. So what happened? Why were these fires so much different than the fires earlier in the 2017 fire season? Well, let's talk about, first, how these fires occurred. Now, most of these fires have been associated with utility-caused ignitions, meaning they're power line fires. And utility-caused ignitions are one of the ignition sources that increases dramatically as wind speed increases, because vegetation comes into contact with lines. The lines can actually slap together and drop burning or molten particles, metal, burning fragments onto the ground, that type of thing. Now, I'll show a movie here of the ignition of these fires that happened starting around 9 to 10 o'clock at night on the 8th of October. So what you'll see as this starts to move, this is an infrared depiction of hot spots, and watch the time. Around 9 to 10 o'clock at night, we start to see these hot spots developing across Northern California. The complex here, this is the wine country fires, or the North Bay fires as they're sometimes called. The kind of rapidly spreading blob is the Tubbs fire. So what you have is near simultaneous ignition of literally dozens of fires across all of Northern California. And this happened around 8, 9, 10 o'clock at night. By the time the sun came up the next day, most of the damage from those fires had already occurred. Now, as far as the winds that developed, this was a major wind event that impacted much of Northern California. And I've done a reconstruction using the weather modeling tool called WRF, which is Weather Research and Forecasting. And this is a commonly used tool both for weather modeling as well as for developing climatological inputs for fire modeling. And I want to just point out that the major fires are called the wine country fires because they ignited across Sonoma and Napa counties, which are two of the major wine producing regions in California. And so those fires, a lot of them ignited very close to the border between Napa and Sonoma County, which you can see here. And what I'm showing here is the modeled wind speed as a function of time across much of Northern California. So by 6 p.m., any of these areas that are in red would be sustained wind speeds above about 30 miles per hour. And so as the night goes on, what we can see is that these areas of high wind speeds are progressing to the south and to the west and begin to impact Napa and Sonoma counties around 8 or 9 p.m. And we see very strong wind speed starting to develop around 10 p.m., which not coincidentally is when several of these fires were ignited. So by 11 p.m., most of these fires have now ignited. They're now spreading under the influence of 30, 40, 50 mile an hour winds. So this was a wind-driven fire event. That's one of the reasons why the impacts were so severe. And I'll just show some footage that was taken from inside the fire. So one of the things that happens when you have wind-driven fires like this is there are showers of embers. Sometimes it's described as a river of embers. And so you can see here, you have burning structures, you have burning vegetation, and there's just hundreds of millions of embers that are just going wherever the wind is driving them to. And it's actually these embers that are largely responsible for many of the structure losses. It's often not direct flame contact or direct flame impingement. It's usually this shower of embers. Here's another view from inside the Tubbs fire. This is from the Sonoma County Sheriff's Office. And again, you get the sense that there is a significant amount of embers being generated. And also, I just want to point out the nature of the winds here. In some cases, they're blowing from left to right. In other cases, they're blowing from right to left. So these gusty, unpredictable winds are also another characteristic of these type of fires. Now, in terms of the damage, there were entire areas of Santa Rosa that were basically destroyed. So this is one of them. And this photo here, this is ortho imagery from prior to the fire. And we can then move forward in time to after the fire. And with one exception, this home here, all the houses in this particular area were destroyed. Now, there's been much talk about a neighborhood called Coffey Park. This is Coffey Park to the left. The red here is the ultimate perimeter of the Tubbs fire. And you'll note a Kmart in the sort of upper right part. Now, I'll do the same thing where we'll move forward in time and look at what this looked like after the fire. And you can see that most of the neighborhood of Coffey Park was destroyed. And something that's very unusual is this Kmart was destroyed. It's very unusual to lose commercial structures such as that in wildland or wildland-urban interface fires. But what had happened here is the suppression resources were drawn down. There was very little water pressure available. And so in addition to losing many, many homes in the Coffey Park neighborhood, there were some commercial structures that were lost as well. Now, one of the interesting things about this that's received a lot of attention in California is that this neighborhood of Coffey Park is outside of what's called a very high fire hazard severity zone. And the very high fire hazard severity zones are significant because they trigger certain wildland urban interface requirements when building single family homes in California. Now those requirements come in only for structures inside the very high fire hazard severity zone. And because Coffey Park is outside of a very high fire hazard severity zone, it's actually being rebuilt without the wildland and urban interface requirements, without California's Chapter 7A of the building code. So that's an interesting thing. We'll have to see if that ends up being a wise decision or not. In terms of some other pre-fire, post-fire kind of photographs, this is another neighborhood in Santa Rosa called Fountain Grove. And you can see that many of these structures, a very high percentage of these structures were all destroyed. So this brings us to the next part of the talk, which is, can we identify areas where this could happen again? Can we map areas that are at an elevated risk of experiencing this type of damaging fires? So some perspective. First, I did this work in 2016, and this was submitted to the IFSS meeting, and it was published in a paper. And so at the time that I did this work, we only had the 2015 and 2016 fire seasons to talk about. So in 2015, the Valley Fire destroyed almost 2,000 structures. Butte was over 900 structures. And then 2016, the Erskine and Blue Cut fires occurred with, I guess, about 700 or 800 structures in total between the two of them. Now, subsequent to doing this work, the 2017 fires, and then we'll talk a little bit about the 2018 fires as well, occurred. And these numbers, the trajectory is not in the right direction here. The trajectory is in the wrong direction insofar as these numbers keep getting bigger. And so the question is, can we figure out where these fires or this type of fire might happen again? Now, there's a number of ways you can do this. The way that I chose to tackle this problem is using a Monte Carlo analysis. So this basically takes millions of fires and distributes them randomly across the landscape in California, and then we model their progression under historical wind and weather conditions. So this is a very large scale analysis. It has lots and lots of inputs. I'll talk about some of them. So the obvious ones are topography and then fuel layers. These come from a program called Landfire, which I'll talk a little bit about. We need a gridded transient description of fire weather. That comes from the weather research and forecasting model. And because we're quantifying impacts to structures, we also need a housing density map or a structure density map. And there's a few different ways you can do this. I used data from the US Census. So the basic idea is you roll the dice, or you pick an ignition location randomly, and then you roll the dice again, and you draw a weather stream, and then you model the progression of the fire, record how big it gets, how many structures it impacts, and so on. And then we can pull different outputs out of this model and use it to quantify risk. And I'll walk through those steps in some detail. A little bit of a background on wildland fire modeling. This could be a whole webinar. The tool that we use is called Elm-Fire, which is I guess it's not quite an acronym, but it's stands for Eulerian Level Set Model for Fire Spread. Level set methods, they're a class of numerical techniques that can track surfaces, and it's done on a grid. So Eulerian is just a fancy word for grid or a fixed frame of reference. And the way that the model works is we have a burned area that's separated from an unburned area by a fire perimeter, and at each point along the fire perimeter, the model tracks things like slope, wind, fuel type, and uses that to calculate the spread rate as well as the direction of spread at that fire front. So what you get at the end, or after you run the model, we have an ignition here at the base of, this is Mount Diablo in Northern California. We have a progression or a perimeter that's developing, and we can take this and tabulate whatever is inside that perimeter, houses, other structures. So we're doing this, we're igniting fires and modeling their spread, but rather than doing one as we're showing here, we're doing about 110 million across California. So in terms of the inputs, there's a few main areas: fuels, weather, and topography. And several years ago, the California Public Utilities Commission undertook a project to map the environmental variables that affect fire in California. And so they actually developed a quite comprehensive climatology where there was 10 years, 2004 to 2013, of very high resolution, 2 kilometer, which is considered high resolution for weather modeling, wind speed, temperature, wind direction, everything you need for fire modeling for 3,653 days. So this was almost an unprecedented type of climatology, and it provided a really good opportunity to take this and extract some significant fire weather days and then use that to drive Monte Carlo simulation. So this was distilled to a small subset. So we took, instead of those 3,653 days, something like 100 days, because most of those days are inconsequential from a fire weather standpoint. And then we used those sort of near worst case scenario days to drive the fire modeling that I talked about, and we'll show in detail in just a bit here. So just to give an idea, these are some fields that come out of this climatology that was developed using WRF. So wind speed on the left, temperature on the right, and remember these are changing every hour. So we have a high resolution 2 kilometer hourly description of all these fields across California. So they can be used to calculate things like dead fuel moisture content, live fuel moisture content, all these other inputs that are needed. So that's the climatology or the weather side. Now, in terms of fuels, there is a program that I mentioned before called Landfire, and Landfire is a program that maps at 30-meter resolution, about 100-foot resolution, all of the inputs that one needs for conducting fire modeling, because the Forest Service and other agencies use this type of modeling to plan suppression resources, to plan suppression activities, as an example. So here what we're looking at is the distribution of fuel type across central and northern California. So areas that are black would be urban or built up areas. You can see that in San Francisco and in the San Francisco Bay Area. The pink areas are agriculture. The kind of tan or yellowish areas are grass and shrubs. The dark green is timber. The dark gray is barren or non-burnable areas. So we have a very high resolution description of not just surface fuels, but also canopy fuels, because those are important for fire propagation. And we also have at the same resolution description of topography. So we have rasters that describe elevation, slope, and aspect, which is the direction that a slope faces. So all of those are necessary inputs for the fire spread modeling. So this all comes from Landfire. Now, I mentioned before we're calculating or we're tabulating risk associated with structure loss. So we need a description of where houses are. And the US Census is actually quite a good resource for this. The census blocks are fairly fine-grained. So as an example, California has about 425,000 square kilometers of land mass, and it's got about 710,000 census blocks. So just to give an idea of the distribution of population within those census blocks, on the left is the Butte Fire. I should have put a scale here, but it's about 70,000 acres, 71,000 acres, something like that. And then each of the polygons in there is a different census block. So you can take the census data, which gives you number of structures in a census block and also its area, and just divide the number of structures by the area to get a structure density. And so on the right, I've shown the housing density in the Butte Fire. So the point here is we don't have exact, precise locations for where structures are, but we do know at the census block level where structures are. So we're modeling impacts to structures at the census block level, not at sort of the neighborhood scale or the neighborhood level. So those are the inputs. Now, how do we quantify risk, right? Because what's coming out of the fire model is things like fire area, number of impacted structures, and so on. So I talked a little bit about the methodology, but just as a, to kind of repeat or emphasize what we're doing here, it's really a a Monte Carlo simulation where we're putting ignitions down at a density of about 1 per acre. We're then modeling for each ignition location spread under that 10-year climatology, under a certain day of that 10-year climatology. And then we're calculating fire area, average flame length, number of impacted structures, and so on for each ignition location. And then this is done over 100 million times for California for a statewide run. So in terms of quantifying risk, well, there's really 2 legs to the risk equation. The first is likelihood or probability, and then the second is consequence or impact. And the highest risk occurs where the likelihood and consequence are the highest. So how do we quantify likelihood or consequence? Well, likelihood is a little bit more difficult than consequence. Consequence is the number of impacted structures. That's fairly straightforward. But if you think about likelihood, the likelihood of a fire becoming a large campaign fire, meaning a multi-day or multi-week fire, has to do with whether or not that fire is put out right away. In other words, if a fire is caught at 1 acre or 5 acres and extinguished, it doesn't go on and become a 10,000 or 20,000 acre fire. But the fires that are most likely to get big are those that spread quickly and escape initial containment efforts. So we said, all right, well, let's say that the likelihood of a fire escaping its initial containment efforts is proportional to fire volume. Now, fire volume is the area of a fire multiplied by flame length, with the idea being that if you have a short grass fire, if you have a grass fire that burns with short flame lengths, 2 or 3 feet, that's significantly different than if you have a chaparral fire burning with 50-foot flame lengths. So we're going to say here that likelihood, as far as the risk equation goes, is related to fire volume, or is proportional to fire volume, whereas consequence is the number of impacted structures. So I'll show a few different plots of likelihood, consequence, and then risk. And I've normalized this by percentile. In other words, rather than showing the raw scores here, everything is normalized relative to all the other pixels in California, so that the bright red areas are 95th percentile or higher, and then the blue areas are going to be lower. So this is the relative likelihood of a fire escaping initial containment efforts based on this 100+ million ignition simulations. And we can go and then look at consequence. So consequence is going to look different because this now takes into account population distribution. So if you have areas where the conditions are such that you can have a rapidly spreading fire, that's not necessarily going to correlate to high consequence or potential for impacted structures if there's no structures there. So that's why these 2 look very different. And then to calculate overall risk, we just use the actuarial definition of risk, which is probability times consequence, multiply those 2 together, and then here's the overall risk of structure loss in California, again, normalized by percentile. So what we can do now is pull out the highest risk areas and start looking at how those correlate with historical damaging fires. So as I said, when I first did this work, it was 2016. And what I did was try to pull out an area that was capable of capturing most of the historical damaging fires that had occurred to date. So as of July of 2016, this is the top 20 most damaging fires in California. This is a sort of a running list that is tabulated or kept by CAL FIRE, and it's updated every time there's a fire that makes its way onto this list. So at the time, the most damaging fire in California history was the 91 Tunnel Fire, or the Oakland Hills Fire, which had destroyed just under 3,000 structures. And what we can do is take perimeters for those 20 fires and then overlay them on a map. And so what I did was I took the highest 20% of the overall risk, which is these orange areas. So I took the pixels that were higher than 80% of all the other pixels in terms of their risk score and colored them orange, and then took fire perimeters and colored them blue and then overlaid them. And it's hard to see at the state scale, but if you zoom in and look at Southern California as an example, what you can see is that all of these large loss fires fall within this orange area that's approximately the top 20% of risk in California. So that's for Southern California. And then here's for Northern California. So Valley Fire, Butte Fire, Humboldt Fire. If anybody's interested, this is where Paradise is. The Humboldt Fire burned into Paradise in, I believe, 2008 kind of time frame. And the point here, the takeaway is, well, look, all these fires fall within the orange area. And that's because this orange area is quite large. It's about 20% of the total landmass of California, but we had to cast a net that large to be able to capture all these fires. In terms of the 2017 fires, we can do the same thing, where we can take these fire perimeters and do an overlay. And here is the 2017 list, or the list updated for the fires that occurred in 2017. Again, this is the date here is 1/12/2018. So we have all of the North Bay fires from 2017. Tubbs, Nuns, Thomas happened in Ventura and Santa Barbara counties in December. It wasn't one of the North Bay fires. Atlas and Redwood Valley. So here are 1, 2, 3, 4, 5 fires that made their way into the top 20. And so what we can do then is same kind of overlay. And it's not surprising that all these fires occur in areas where there are these very large, or where there's a predominance of these orange pixels, which correspond to the top 20% of the overall risk. So if we go on, we can look in Southern California at this is the Thomas Fire. And the Thomas Fire is the one that burned all the way to Montecito and ultimately caused the mudslides. But again, what you can see is that we're capturing most of that perimeter within these orange areas. Now, if we go on, you can see I'm going to have to update this almost every year, probably, unfortunately. 2018 fires. This list keeps changing. We've now got the Camp Fire as the most damaging fire. And then we've also got Woolsey and Carr that are now on the list. So we can, again, do the same type of thing. I put some ortho imagery in here to make it a little more interesting. The lower fire is the Camp Fire, which started outside of Paradise and burned into Paradise under winds out of the northeast blowing toward the southwest. And almost the entire footprint falls within these orange pixels. The upper fire is the Carr Fire, and this one is interesting. Most of the structure losses were in the southeast part of that fire perimeter on the outskirts of Redding. And what you can see is that much of that fire, the Carr Fire, is actually not covered by these orange pixels. And the reason for that is that much of the areas that were burned by the Carr Fire were largely uninhabited. So the Carr Fire here is a little bit of an outlier in that it does correlate or overlap with some of these orange pixels where there are structures, but much of that perimeter just was burning through largely uninhabited areas. So what about the Woolsey Fire? The Woolsey Fire is the one that burned into Malibu. And what you can see is that, again, most of the perimeter, the ultimate or final Woolsey Fire perimeter, does fall within these orange pixels that correspond to the top 20% of risk. So, to kind of tie this up and put a summary on it, we're now at the point where we can actually do a fairly granular, high-resolution analysis of fire risk across large geographic areas. So the computer power has progressed to the point where this is now feasible. The inputs are there. We have fairly good data sets, readily accessible data sets that can be used to do this type of mapping. And by comparing to historical perimeters, we can show that there's a very good correlation between the areas that are identified as high risk and historical occurrence of damaging fires. But I think that the kind of the scary thing about this is that based on this analysis, it looks like about 20% of California's landmass is capable of supporting this type of large loss fire. That's a fairly large area. So I think this has major implications for future development in California. I think it's something that the fire protection engineering community is just starting to grapple with. And one of the next steps here is to take this type of analysis, and rather than doing it backward looking, meaning based on historical wind and weather conditions, to turn it around and make it forward looking. So in other words, rather than using a past cast or a hindcast for weather conditions, we're using a forecast. So you can look out 3 to 7 days into the future and say, okay, well, we have these conditions that are developing, and the conditions are such that there's a potential for large loss fires in certain areas. And why do you need to know that? Well, one of the things that is a big topic in California now is proactive de-energization of power lines. So if you look at that top 20 list, there are several fires on there that are associated with power line caused ignition. So the utilities now have an interest in not only going through and hardening their infrastructure, but in certain situations where you have high winds, proactively de-energizing the power lines to prevent an ignition and rapidly spreading fires. So that's one reason that there's some interest in this, but also things like allocating resources, allocating suppression resources intelligently, and also ignition prevention. If you can prevent ignition by shutting down logging or other activities that could create ignition sources under situations where there's a potential for rapidly spreading fires, that's a good way to do things. So I think we're going to start to see this type of analysis being done not just for backward-looking conditions, but also what's going to happen if a fire starts at 2 p.m. on Tuesday, kind of thing, and then use that type of information to make decisions about fire prevention, power line de-energization, and so on. So those are the main things I wanted to get through, and I suppose I'll turn it back over to Lewis for questions, discussions, comments.
Great, Chris. Yeah, we do have some time for some questions, so let's get started. The first question we have is, will possible Pacific Power and Light decisions to turn off power distribution during high wind events affect firefighting capability? And then there's an example where fire, water pumping, or water distribution pumping capabilities could be significantly reduced.
Yeah, I think that's a great point, and I don't think we know the answer to that. I would say certainly in some situations that seems perfectly plausible that firefighting activities could be impacted. Let's also not forget that there are other things that related to firefighting and communications that depend on the electrical grid. So one of the things that was reported after the North Bay fires is that most of the cell phone communications basically just didn't work due to deterioration of infrastructure and so on. So there are major implications associated with shutting down the power if you do have an ignition where you do need things that run on electricity. I think it's a hard problem. This idea of proactive de-energization wasn't even on the radar screen until after the 2007 fires in Southern California, and the first organization or first utility to propose this was San Diego Gas and Electric. And at the time, the Public Utilities Commission really was a little bit leery about this. The CPUC has now largely embraced the idea of proactive de-energization as a fire prevention measure.
Great. The next question we have here is, how does this sort of analysis account for fuel modifications, such as fuel breaks, fire breaks, areas maintained with prescribed burning, that would generally be smaller than the grid size you are using with elm fire?
That's a great question. Let me talk about the inputs a little bit. As I said, we and everybody else really who does fire modeling uses inputs from Landfire. Now, Landfire is updated every 2 to 3 years. So if you go and you download the current data, I believe it's through 2014. So any disturbances, meaning fires or other things that affect the landscape that happened in the intervening years are just not included in that fuel input. So there is a little bit of a challenge here insofar as if you have areas where there's been recent fires, like, Northern California last year, we had Carr Fire, Delta Fire, HERS Fire, Mendocino Complex Fire. All those fires have converted several 100,000 of acres of landscape into, if not non-burnable, early stages of recovery where you have grass and things like that. So that is one effect there is recent disturbances are not necessarily included in the fuel layers, but also the underlying length scale is, as I said, 30 meters or 100 feet. And so if you have something that's at a finer scale than that, it's simply not in the inputs. So those fine scale fuel modifications and things like that, defensible space and so on, would not be included in this type of analysis.
Okay, great. Next question is this data available commercially for insurance risk models?
Well, honestly, nobody's ever asked me for it. It's published in a paper in IFSS that I have the rasters. If anybody wants it, I'd be happy to provide it to anyone. But no, it's to the best of my knowledge, the insurance companies are really not doing anything at this scale. If they are, I'm not aware of it, but maybe they are, and they're just keeping it quiet. But no, I don't think that this has really made its way into the insurance industry yet.
All right, great. The next question is, well, first there's a comment noting that this is great work, and then they go on to ask, how did your results correlate with the 5 or 10% of overall risk?
I think what the question is asking is if we take this map and rather than call out the top 20% of risk, if we reduce the size of the footprint and call out the top 5 or 10% of risk, in which case there would be much fewer orange pixels. And what I've found by doing that is that as you reduce, as you sort of turn that dial and reduce the area, you start to not capture some of these fires. So this 20%, although it's kind of a nice round number, is not arbitrary insofar as I had to sort of turn the dial to get it to the point where we would capture most of those fires. But if you do look at some of the worst fires, like the Camp Fire, just as an example, it is in one of the areas that would be captured in that highest 5 or 10% risk.
All right. The next question is, do you know what percentage of California's population reside within this 20% of the landmass?
I do not. That's a wonderful, I'm just going to go back to the beginning to show the population distribution, which is way, way back. But probably what we should do is take this kind of a map on the right that has structure density and just do an area integral for the top 20% of risk to answer that question. I've never thought about doing that. That's a great thing to do. I might do that later today.
Great. The next question we have is, what are the major ignition sources for the past wildfires?
Well, let's go look at the Cal Fire list. What I can tell you is that the ignition sources for damaging fires are not necessarily the same as all ignition sources. So let me go to the most recent list. If we go to the 2000, okay, this is from March of 2019. And if you look at these fires, a lot of them are power lines, and Camp Fire, as we've all heard in the news, is most likely a PG&E, a power line ignition. Woolsey Fire is allegedly a Southern California Edison caused ignition. Carr is not a power line fire, but if you look at these, a lot of these are power line fires. And the reason for that, I sort of alluded to this at the beginning, the mechanisms that cause power lines to create ignition sources only occur, or at least are more likely to occur under high winds, and because branches fall onto lines or lines slap together and things like that. And it's just those same conditions that correspond to rapidly spreading fires. So although power line fires are really only about 2% of total ignitions, maybe closer to 1%, they have a disproportionate place in this top 20 most damaging list of fires. But if you were to look at all ignitions, by large, but in most cases, they're all human caused, or at least a large fraction of them are human caused. So, people doing things, burning debris and driving cars into dry grass and things like that. So a lot of the ignitions are caused by, human factors, people doing things they shouldn't be doing.
All right. Next question we have is, have you taken into account the impact of forest management, such as stopping all fires which allow underbrush to build up, into the fire severity?
The short answer is that would be capable, or we would be capable of doing that if that's reflected in the underlying fuels layers. But because we're using the fuel layers off the shelf, if any recent activities are not reflected in those fuel layers, that would not be included in the modeling analysis. In other words, the models have the capability to account for that if that is reflected in the inputs. If it's not reflected in the inputs, then it's not going to be reflected in the model outputs.
All right. Next question we have is, I saw US Microsoft building footprint data. Do you think combining these two will give a promising result in terms of fire hazards to buildings?
I'm not familiar with that particular data product, but there is something similar in California that CAL FIRE has developed, and this was used in the California Public Utilities Commission High Fire Threat District mapping process. And it's a much more granular description of where structures are based on remote sensing and imagery and so on. And I've also used that data set side by side with the census data to see if the results are significantly different. And there are some differences, but it's not as significant as one might expect. So my sense is that if this Microsoft product is similar to this CAL FIRE product, insofar as it's a more granular description of where structures are, that you may see some differences in where the overall risk shows up, but that it wouldn't be a dramatic difference. You're still going to have hot spots that are driven by fuels, weather, topography, and proximity of people to those factors that control fire spread.
Great. The next question we have is, would rate of spread or flame lengths be preferred over random ignitions when doing risk assessment?
Well, I think that one of the areas, and maybe I'm going to answer a slightly different question. I think one of the areas where this work could be improved is rather than igniting fires uniformly and randomly across the state, igniting them in areas where we're more likely to have ignitions. In other words, the distribution of ignitions spatially across California, or really any geographic region, is not uniform. It tends to follow roads, it tends to follow population, it tends to be, because these fires are largely human caused, it tends to be where there's a higher density in terms of ignitions per square mile per year in those areas. So that would be one area where I think this could be refined. And one of the challenges with quantifying risk from a fire model is the fire models do give us things like flame length or fire size, not necessarily risk. You have to come up with a recipe or a formula to take those outputs and use them to quantify risk. So I think the way that we've done this here is one way to do it. There are probably other ways where you could take these outputs and use them to quantify risk a little bit differently. I think the probability of occurrence is one piece that would strengthen this work and maybe make it a little more broadly applicable, because in this work we ignited fires out in the middle of nowhere in wilderness areas where there's very unlikely to have ignitions because there's just nothing out there other than lightning.
Great. The next question we have is, goes on to state, the perception of an increased wildland fire risk is often tied to global warming. Has there been any discussions about looking back with your model using other than current fuel assumptions to show a global warming correlation to the increased risk?
Well, there is a project that will just be starting within the next couple of months to do just that in California. So the California Energy Commission recently funded a project that will look at fire risk later this century. So in other words, rather than modeling fires in 2004 to 2013, it will be modeling fires in 2050 or 2090 or 2100 based on some assumptions about how fuels will develop between now and then, and where the development will be, and so on. So that work has not been done yet, but the California Energy Commission just funded a $5 million grant with an interdisciplinary research team to look into that. And I think that's a really important thing for planning, is to understand, as we get farther into climate change and global warming, are there areas where this fire problem is just going to become much worse? Or maybe are there areas where there isn't much of a fire problem now, but we think that by 2050 or by 2100 there will be a fire problem. So it's absolutely on the radar screen, at least in California, and I'm sure in other parts of the Western US or the world as well.
Great. Next question we have is, you mentioned lightning as an ignition cause. Of the top 20, were any of them caused by lightning?
I don't think so. I'm looking at the list right now, and I don't think any lightning caused fires are on here. There's actually fairly relative to other parts of the country, there's actually fairly low lightning density in California. That being said, there are situations where a large lightning bust will ignite lots of fires. So one of the best known recent examples was in 2008. At the end of June, there was a lightning bust that ignited several, I think it was around 2,000 fires across California. Now, most of them were pretty small and were put out, but several of them burned for the rest of that summer, basically from the end of June and into September. But they're in largely rural parts of Northern California. There were some structure losses, but it was fairly minimal. So lightning is really not as big of a problem for fire ignitions in California as it is in other areas.
Great. Next question is, has there been any thought given to using such data to plan evacuation either during high wind events or maybe even before ignitions during high wind events?
Yes, there is a that is a topic of discussion, an active topic of discussion, and there is I'm aware of a research group that's working on that, an interdisciplinary team that's looking at using fire spread modeling data in conjunction with evacuation modeling to do just that, where you would phase the evacuation. So, just as an example, on November 8th, the day the campfire started, that wind event was known, it was forecasted to occur. And so, I got up early and started looking at what was happening. And early that morning, there was only one sector of Paradise that was being evacuated. And so the question becomes, well, what if there had been this type of a tool in place where one could forecast the spread of the fire and then do the evacuation modeling side of it and phase the evacuations appropriately. So I think there's some real value in that type of real-term or near real-time fire forecasting, especially coupled with evacuation modeling. One of the challenges here is that these operational fire spread models don't do smoke. And in other words, they're not tracking where smoke is going and how that impacts roadways and things like that. And that can be a big problem for evacuation. So I think there is an opportunity here to make some real nice progress in developing these type of tools that include things that are just not included now, like where is smoke going to obscure roadways?
Great. The next question we have is speaking on the power lines, and if you're aware that power lines being more prone to breakage due to increased power usage, such as hotter weather meaning more air conditioning use, therefore the power lines become more energized and more elastic.
Yeah, that's a little bit beyond my area of expertise, but I do know just sort of anecdotally that does occur. If you have a hot day with lots of usage on the line, there's actually a little bit of sag, more sag in the lines. The catenary curve, which is the shape that the power line takes as it goes from one anchor point to another, changes and can actually sag due to that effect where the metallurgical properties of the conductors are changing.
Okay. The next question we have is, how would you deal with land fire considering current WUI developed zones as unburnable on FASR site? Is there an alternate software for educational purposes?
Okay, let me give some background there. All right, so this is Coffee Park, pre-fire, post-fire. And if you go and you look in land fire, that whole neighborhood is marked as urban, which our fire models treat as non-burnable. So this is a big limitation of all models. There is, to the best of my knowledge, there's really no way to incorporate spread in built-up areas like Coffee Park or Ventura for the Thomas Fire, for example, to incorporate spread through those type of areas into current models. The models that we use, at least the operational models, are looking at surface fuels that are natural fuels. There isn't even a fuel model for this type of neighborhood. So it's a real blind spot, to be frank about it. And there's a lot of interest in developing models that can actually simulate progression through built-up areas like Coffee Park. But that's beyond the capabilities of the current generation of operational fire spread models. You might be able to do something with a computational fluid dynamics based model like WFDS to model structure-to-structure fire spread, but it's just not included in our current models.
Great. The last question we'll have time for, it might be a little bit of a lengthy one, but can you discuss extrapolation to other states? And they're throwing out Florida as an example for a state to discuss.
Yeah, so I talked about California in this presentation or webinar, but we've actually done modeling for a large part of the Western US to understand this same type of risk, not just for California, but Oregon, Washington, Utah, Idaho, Wyoming, Montana. Large parts of those states have been mapped similarly, and the process is the same. It's really, step one is develop your climatology. That could be from a weather model. It doesn't have to be, though. It could be from weather observations. Step two is get your, all your inputs, your fuels, your topography, and then step three is run the, the analysis. And step four is combine the inputs and, using some recipe to quantify risk. But, one of the kind of pipe dreams that I have is I think that a national, meaning for the continental U.S. or maybe continental U.S. with, Alaska and Hawaii as well, a map of, or some type of a description of the areas where there's a real wildland-urban interface fire problem would be necessary or would be helpful, because right now, although there's WUI codes, the WUI codes say, this will be enacted in an area designated by the authority having jurisdiction. And the problem is that the authorities having jurisdiction don't necessarily have an off-the-shelf product that they can go to and say, all right, well, here's the areas where we have to worry about wildland-urban interface fire risk. In California, it's a little bit different because CAL FIRE has done that. CAL FIRE has mapped, through the very high fire hazard severity zone process, the areas where the wildland-urban interface requirements apply. But I don't think that there's an analogous product for the rest of the U.S.
All right. Before we end today's webinar, I'd just like to make an announcement that SFP will be offering a 2-day Protecting Flammable Combustible Liquid seminar next week, May 21st and 22nd in Toronto, Canada, at Seneca College. You can find more information on our website, sfp.org. And then thanks to everyone who participated in today's webinar, and thanks again, Chris, for an outstanding presentation.
My pleasure. Thank you.